Welcome to today's deep dive. When you step onto a commercial flight, there is this almost theatrical illusion of freedom. You settle into your seat, the engines hum, and suddenly you're defying gravity, right?
Yeah, you're just soaring through the clouds. It feels completely limitless.
Exactly. It feels like magic. But for the professional pilot sitting, just a few feet away in the cockpit, the reality is entirely different. For them, flying is this strict, unyielding science.
Oh, absolutely. They aren't just flying a plane. They are operating inside what is essentially an invisible mathematical cage.
An invisible cage. I like that. Because every single second, they are surrounded by absolute numerical boundaries that dictate exactly what they can and cannot do just to keep you safe. So today, we're taking a highly technical stack of documents, specifically excerpts from the Airbus A318, 319, 320, and A321 Flight Crew Operating Manual.
Right, the FCOM, as it's known in the industry.
Yeah, specifically the chapter on limitations.
Yes.
And our mission today is to examine the strict physical rules these professionals operate under.
And this manual forms the literal, legal, and physical envelope of the aircraft. I mean, these numbers are the hard lines drawn by the manufacturer that basically say, if you step outside these boundaries, we can no longer guarantee the structural integrity of this machine.
Which is terrifying, but also amazing. So we're going to look at how these raw data points translate into the precise physics of flight that pilots manage while, you are just sitting in the cabin sipping your ginger ale.
Exactly. And the manual begins by defining the absolute maximum limits of the aircraft when it's high in the sky.
Right. It establishes two distinct speed limits, which I found fascinating. There's the maximum operating speed, or VMO, at 350 knots, and then there's the maximum Mach number, or MMO, of Mach 0.82.
Yeah, having two different metrics for speed implies that the aircraft faces two entirely different physical threats depending on, how fast it's moving and where it is.
So break that down for us. What is the VMO protecting us from?
Well, the VMO of 350 knots, which is roughly 400 miles per hour of indicated airspeed, that's really about dynamic pressure. At lower altitudes where the air is thicker, ramming the aircraft through the atmosphere at high speed puts immense physical force on the windshield, the wings, the tail.
So it's literally just the brute force of the wind pushing against the metal.
Right. If you exceed VMO, you risk structural damage just from thick air. But as the aircraft climbs higher and the air thins out, that indicated airspeed naturally drops. That's where the MMO of Mach 0.82 takes over.
Mach 0.82 meaning 82% of the speed of sound, right?
Exactly. Because as you approach the speed of sound, the airflow accelerating over the curved top of the wing can actually reach supersonic speeds.
Wait, really? The air over the wing goes supersonic before the plane itself does.
Yeah, it creates these localized shock waves, and those shock waves disrupt lift and can cause a phenomenon called Mach tuck, where the nose pitches down violently. So basically, VMO protects the plane from being crushed by thick air, and MMO protects it from the aerodynamic chaos of the sound barrier.
Wow. And the manual specifies that the aircraft can push these speeds up to a maximum pressure altitude of 39,800 feet.
Almost 40,000 feet up.
Which is crazy when you think about it. I mean, that's nearly 2 miles higher than the summit of Mount Everest. The environment up there is lethally thin and incredibly cold. So if the plane is nearly 40,000 feet up, how does the manual dictate we protect the fragile humans inside?
Well, to keep people alive, the aircraft pumps bleed air from the engines into the cabin, but doing so basically turns the fuselage into a pressurized balloon.
A very heavy metal balloon.
Exactly. And the manual draws a hard line here. It states the maximum positive differential pressure is 9.0 psi, or pounds per square inch.
9.0 psi, that doesn't sound like a lot on its own.
It doesn't, but that 9.0 psi is the mathematical limit of the aircraft's skin. It represents the difference between the breathable atmosphere inside the cabin and the near vacuum outside. 9 pounds of outward force on every single square inch of the fuselage.
Oh, wow. Every square inch.
Yeah, that adds up to hundreds of thousands of pounds of pressure trying to rip the aluminum apart. The fuselage is constantly expanding and contracting with every flight. It's a cycle of metal fatigue.
So the 9.0 psi limit ensures the metal doesn't stretch beyond its elastic limit.
Precisely. To manage this, an automated outflow valve in the rear of the plane constantly opens and closes, regulating the pressure to ensure the cabin altitude never exceeds 8,000 feet, regardless of how high the aircraft actually climbs.
Right, so maintaining that sealed environment is critical at 39,000 feet. But what really stands out in the FCOM is that managing the air inside this sealed tube is just as strictly regulated on the ground.
Oh, yeah, the ground limits are surprisingly strict.
Yeah, the manual states that with passengers on board, the crew is not recommended to exceed 20 minutes without an air conditioning supply.
Which is highly relatable for anyone who's been stuck on a tarmac. A parked airplane in the sun is essentially a sealed greenhouse.
Right, because without the air conditioning packs actively circulating and filtering the air, the collective, metabolic output of 150 passengers causes carbon dioxide levels and temperatures to just spike rapidly.
It gets uncomfortable real fast. And that 20-minute limit is a physiological boundary to prevent the environment from becoming literally toxic before the engines are even turned on.
It really highlights how reliant we are on the aircraft's systems to artificially sustain a habitable environment.
We really are. But once the aircraft pushes back from the gate and prepares for takeoff, the pilot's focus has to shift from the internal environment to the external one.
Right, because the air up at 39,000 feet is thin and cold, but the real challenges happen closer to the ground where the weather lives. Which brings us into how pilots battle the elements, specifically wind.
Wind is a massive factor. When an aircraft is taking off or landing, it's highly susceptible to lateral forces. The manual sets the maximum demonstrated crosswind, meaning wind blowing perpendicular to the runway at 38 knots for a normal dry runway.
38 knots. That is a significant force pushing against the side of the plane.
It is. But the friction of the tires on a dry runway allows the plane to track straight. The rubber grips the asphalt.
But the manual details how this plummets based on runway conditions, right? Like if you change the surface friction, you fundamentally change the physics of the landing.
Completely. The manual dictates that if the runway has compacted snow, the crosswind limit drops to 29 knots.
Okay, that makes sense.
But if the runway is covered in ice, specifically cold, dry ice, the limit clashes down to just 15 knots.
Okay, wait a minute. 15 knots is around 17 miles per hour. That doesn't sound very fast for a massive jetliner. Why does a little bit of ice make the aircraft so vulnerable to crosswinds?
It's a perfect illustration of aerodynamic leverage. So an Airbus A320 has a massive vertical stabilizer, right? The tail fin.
Right, the big fin on the back.
Yeah, and it sits far behind the aircraft's center of gravity. That tail basically acts like a giant sail. When a crosswind hits it, the wind tries to push the tail sideways, which pivots the aircraft around its center of gravity.
Ah, I see. On a dry runway, the heavy rubber tires grip the asphalt and resist that twisting force. But on cold, dry ice, the coefficient of friction drops to near zero.
So there's nothing holding it straight.
Exactly. If a 15-knot wind hits that tail, there's no grip to counteract the push. The airplane will weather vane. It'll violently snap its nose into the wind and just slide laterally off the runway. The sheer physical weight of the aircraft cannot save it if there's no friction to anchor it.
That is terrifying. The physics of that are so unforgiving. It's just pure traction versus surface area. And, the weather dictates the limits of the aircraft's physical components in the air just as strictly.
Oh, yeah. Like the windshield wipers?
Yes. The manual specifies that the windshield wipers have a maximum operating speed of 230 knots. I mean, the motors required to drag rubber across glass while fighting a 260-mile-per-hour headwind must be incredibly robust.
But even they will stall or snap above that speed. And then there's some really quirky weather limits, like the cockpit window itself has a maximum opening speed of 200 knots. Which begs the question, why are you opening a window at 200 knots?
Right. Well, opening a window in flight is basically your ultimate worst-case scenario backup. If the forward windshield is completely obscured by a bird strike or severe icing that the heaters fail to clear or an engine oil leak, the pilots need a way to physically look outside to see the runway.
So they just roll the window down like a car?
Kind of. But the 200-knot limit is dictated by Bernoulli's principle. The air rushing over the nose of the aircraft creates an intense low-pressure zone on the outside of the glass.
Right, a vacuum.
Yeah, an aerodynamic vacuum. If the pilot unlatches that window at a really high speed, the pressure differential will violently suck the heavy window assembly outward into the slipstream.
Oh, wow. So it can just rip out of their hands.
Exactly. The 200-knot limitation ensures that the vacuum isn't strong enough to warp the window tracks or rip the frame out of the fuselage.
So the manual basically forces the pilot to slow the aircraft down to a survivable aerodynamic state before they compromise the outer shell. But, if the weather gets so bad that the visibility drops to near zero, like a dense fog or a blinding blizzard, sticking a head out the window won't help anyway. The human eye just can't penetrate the weather.
And that physically forces the pilots to hand control over to the computers. They have to rely on instrument landing systems, or ILS.
Right, which shifts the conversation to the strict rules governing automated systems. the auto flight system limitations.
Yeah, the manual categorizes these automated landings into Category 2 and Category 3. So a Category 2 approach requires a minimum decision height of 100 feet. The autopilot flies the plane down the radio beam, but if the pilot cannot visually confirm the runway environment at 100 feet above the ground, the manual mandates an immediate abort.
You have to pull up.
Exactly. But Category 3 approaches are where the engineering becomes truly staggering. Category 3 is divided into fail passive and fail operational. For fail passive, the decision height drops to 50 feet.
And the terminology here is so interesting. Fail passive versus fail operational points to the internal logic of the aircraft's computers, right?
It does.
Fail passive means that if one of the redundant autopilot systems detects a fault during the descent, it will simply disconnect itself without making any sudden, jerky control inputs. It fails in a passive state.
Right, leaving the aircraft stable but forcing the human pilot to instantly take the yoke and execute a missed approach. That's why they still need that 50-foot decision height. The human needs a split second to react.
But then there's fail operational.
Yeah, fail operational represents the highest level of automated redundancy. In this approach, there is no decision height. None.
Wait, zero.
Zero. The aircraft can land completely blind, requiring only a minimum runway visual range of 75 meters, just so the pilots can navigate the taxiways after they roll out.
That's incredible. How does it do that?
The mechanism relies on 3 separate autopilot computers independently calculating the landing. They constantly vote against each other. If one computer generates a faulty calculation, the other 2 recognize the discrepancy, outvote the failing unit, lock it out, and continue the landing sequence uninterrupted. The system survives its own failure.
It remains operational, hence the name. But here's where I have to push back a bit. I noticed a discrepancy in the wind limitations here.
Oh, really?
Yeah. We established earlier that a human pilot is certified to land the plane with a 38-knot crosswind. But the FCOM strictly caps the maximum crosswind for an automatic landing at just 20 knots. Shouldn't the super smart triple redundant computer be better at handling wind than the human?
It's a great question, and it really comes down to the strict parameters of aviation certification. When regulators certify an automated landing system, they demand mathematical certainty.
Okay, meaning what?
Well, the computer relies exclusively on localized radio beams sent from antennas at the end of the runway to legally guarantee that the aircraft will touch down inside a precise painted box on the runway every single time. The certification agencies limit the crosswind to 20 knots. Beyond that, the computer's rigid control laws might overcorrect or fail to maintain the center line perfectly.
Right. It lacks nuance.
Exactly. A human pilot, by contrast, possesses fluid intuition. A pilot can feel a gust, anticipate the sway, and apply a technique like crabbing, where they point the nose into the wind or slipping the aircraft. They are constantly adjusting control pressures right up to the moment the rubber meets the tarmac.
So humans are actually trusted with higher crosswinds than the machines.
Yeah, the human envelope is wider because human judgment can dynamically adapt to chaotic air in a way strict algorithms just cannot legally be certified to do.
The machine operates in a binary state of absolute certainty. If the variables fall outside the certified box, it refuses to play.
Yep. And this reliance on the physical environment explains a highly specific geographical prohibition in the manual, too.
Oh, right. Buried in the auto flight system section, the text states, automatic landing is not permitted on Johannesburg's 03R21L runways. Out of all the airports on Earth, this specific stretch of tarmac is blacklisted for the autopilot.
It's such a fascinating exception. Automatic landings require pristine VHF radio signals to guide the aircraft down the glide slope. And these signals are broadcast from the ground, but topography heavily influences how those radio waves travel.
So if there are hills or buildings?
Exactly. If an airport has uneven terrain, steep drop-offs before the runway threshold, or large reflective structures nearby, the radio signals can bounce and scatter. This creates what's called a bent or warped ILS beam.
And the autopilot just blindly follows it.
Yeah, the autopilot will faithfully follow that warped beam, which could lead the aircraft to pitch erratically or touch down short of the runway. So, the manual permanently restricts automated landings at Johannesburg 03R21L because the local geometry of the Earth there physically prevents the radio antennas from broadcasting a clean signal.
It doesn't meet the legal tolerances.
Right, not for a Category 3 touchdown.
Wow. So whether a human or a computer lands the plane, eventually the rubber has to meet the tarmac, which shifts our focus to the massive forces and limits involved in ground operations: tires, brakes, and weight.
Weight is a huge one. The FTAGAM lists the maximum takeoff weight at 97,000 kilograms, but the maximum landing weight is capped significantly lower at 79,200 kilograms.
That's a gap of nearly 18,000 kilograms, which just accounts for the weight of the fuel the aircraft burns during its journey.
Right, because the structure is engineered to lift 97,000 kilograms smoothly into the air. But slamming that same weight down onto the concrete at 150 miles per hour would exert catastrophic force on the landing gear.
The kinetic energy is just too high.
Exactly. Now, if an aircraft experiences a severe emergency right after takeoff, like an uncontained engine failure, and must return immediately, the pilot will be forced to perform an overweight landing.
Which is permitted, but they have to be incredibly careful.
Yes. The touchdown must be incredibly shallow to avoid snapping the main gear struts, and they'll need virtually the entire length of the runway to stop.
Speaking of stopping, arresting that massive forward momentum brings us to the brakes. Converting the kinetic energy of a 79,000 kilogram machine moving at landing speeds into zero motion involves the carbon brake assemblies generating pure heat.
Immense heat?
And the manual imposes a strict limitation before the aircraft can even begin its next flight. The brake temperature must read below 300 degrees Celsius, with the brake cooling fans off before they can start the takeoff roll.
Right. And to understand the 300-degree limit, you have to look at the physics of a rejected takeoff. Say the pilot accelerates to 150 miles per hour, reaches the point of no return, and an engine violently fails.
You slam on the brakes.
At maximum pressure, the brakes will absorb a staggering amount of kinetic energy in a matter of seconds. If the brake assemblies start that takeoff roll already heat-soaked at, say, 400 degrees from the previous landing,
They just melt.
basically, adding the thermal load of a maximum weight rejected takeoff will push the carbon disks past their thermal limit. They will lose their ability to create friction, which is called brake fade, or they could literally shatter or catch fire.
Oh, man. So the 300-degree cap guarantees they have enough thermal capacity remaining to absorb a worst-case scenario. The numbers are always calculated for the absolute worst case.
Always. And this logic applies to tire emergencies, too. That FCOM provides a strict script for getting the plane off the runway if it blows a tire.
Yeah, I saw this. If one tire per gear is deflated, the max speed is restricted to 7 knots. But if 2 tires are deflated on the same main gear, it's restricted to a crawl of 3 knots. And the nose wheel steering angle is restricted to a maximum of 30 degrees, down from the normal 85 degrees. Why 30 degrees?
Well, the landing gear is a bogie, a central strut with multiple wheels. When 2 tires on one side are flat, the aircraft is essentially dragging metal rims on concrete.
The friction must be unbelievable.
It is. If the pilot attempts to turn the nose wheel at its normal sharp 85-degree angle, the aircraft will try to pivot tightly. But because the flat tires are dragging and refusing to roll, that tight pivot applies massive torsional shear stress to the main landing gear strut.
So a sharp turn could literally twist the heavy metal leg right off the aircraft.
Exactly. The 30-degree steering limit forces the pilot to make incredibly wide, sweeping turns, preserving the structural integrity of the gear.
That makes total sense. And even the smaller systems operate under these strict limits, like the auxiliary power unit, the APU.
Yeah.
It's like trying to start a stubborn lawnmower. The manual says you only get 3 consecutive start attempts, and then the crew must wait a full 60 minutes before trying again.
Yeah, the APU uses a powerful electric starter motor to spin the heavy turbine blades. Cranking that motor draws massive electrical current, generating intense heat. If it fails to start, doing it 3 times, heat soaks the internal components.
So the 60-minute timeout just lets the heat dissipate.
Right. Attempting a forced start without waiting would melt the copper windings inside the motor or cause the turbine blades, which expand when hot, to scrape against the engine casing.
So many quirks. Speaking of quirks, to wrap up the technical specs, there's some highly peculiar prohibitions. Like, the use of mobile phones is strictly prohibited in the toilets and the cockpit. The cockpit makes sense, but why the toilets?
It's very specific, right? The rear toilets are situated against the aft pressure bulkhead. That area is routed with dense, unshielded wiring for the tail surfaces and the flight data recorders. An actively transmitting cellular device in that metallic enclosure could cause electromagnetic interference with the sensor data relaying to the cockpit.
Unbelievable. And then there's a geographical oddity. In the airspace of the Russian Federation, aircraft can only fly on routes covered by ATC ground facilities.
Yeah, that's a geopolitical technological limit. The aircraft is legally prohibited from relying entirely on satellite GPS to navigate through that airspace. It has to remain within physical line of sight of ground radar installations.
So the host nation can positively track the aircraft themselves.
Exactly.
Well, this has been an incredible deep dive. To summarize, the role of a professional pilot is a continuous, unbroken exercise in operating within hundreds of strict, intersecting mathematical limits. From knowing exactly when a 15-knot crosswind turns a multi-million-dollar aircraft into a frictionless weather vane, to managing 300-degree brakes.
Right. The invisible cage we discussed isn't designed to constrain the pilot, it's engineered to eliminate the unknown. The manual forces the chaotic nature of the atmosphere into a predictable mathematical box. So for you, listening to this, the next time you board a flight, appreciate that every slight adjustment, every weight on the tarmac to cool the brakes, every bump in the descent, it's carefully calculated against a master set of rules designed to keep you perfectly safe.
It really redefines what it means to sit in the cabin. But I want to leave you with a final thought to ponder. Consider how these FCOM manuals must constantly evolve. With climate change potentially altering global wind patterns, intensifying thermal heat waves, and changing the frequency of extreme weather, the physical environment outside the aircraft is becoming more extreme.
Oh, absolutely. The atmosphere is changing.
Right. So how might the rigid physical limits of these aircraft, the crosswind limits, the thermal capacities we just discussed, how might they have to adapt in the near future to keep up with the rapidly changing sky? Will the invisible cage have to shrink? Or will aviation engineering find a way to expand it? Just something to think about the next time you hear those engines spool up.